Okay, welcome back. So today we're going to be doing a nodal example. This circuit should look familiar to you from the mesh example that we just covered. As mentioned in that example, I'm not going to be walking through all the explicit algebra. However, I will be setting up the equations. Keep in mind that a bulk of the work is going to be done in setting up the equations, so I want to put more emphasis on that rather than working through the algebra. Along the way, though, I will provide tips and tricks on how to simplify the equations. So, starting off, just like with any other circuit, I want to take a minute to visualize what I have in front of me. So, right away, I'm going to notice that I have my V naught in this, and I have my V delta. So, it is my job to find V naught and V delta within the circuit. Now I can see that V naught is going to be this voltage right here, and V delta will be this voltage right here. Now, contrary to the mesh example, we had to do a little bit more tedious algebra to get us to where we wanted to define these. However, just by simply defining this node voltage right here as V1, this node voltage of this resistor as V2, and this node voltage as V3, this one as V4, I can easily just make the approximation that V2 is equal to V naught. I could have just as easily called this V naught. I could have just as easily called this one V3. So with that being said, I'm going to stick to the sign convention that I have right now. Now again, when analyzing the circuit, I see two sources. Now they are prime for writing a supernode. So if you aren't comfortable with supernode or the concepts, please revisit my first video. I believe it's called Nodal method. So I can briefly go over it. So basically when we write a supernode, we're going to tie up, which is why I have it circled, we're going to tie up this branch, and we're going to write it as if all the currents are coming out of it. All right, just as one. Instead of treating this as one separate, this separate, similar to this one, I'm going to wrap it up, put it in one point, then I'm going to write my currents. You can think of it as that way. All right, and when we write these nodal equations, it will become more apparent to you. So without further ado, let's go ahead and start. Now I'm going to start with my supernodes because those seem to be a little bit more in depth. So let's go ahead and write our supernode for the left. All right, so right away, I'm going to, again, I want to stress it, circle my node, tie it up, start writing currents going out of it. That's a nice way to remember it. All right, I'm going to have my plus 0.003 V delta plus my V1 over my 100 plus my V2 over my 250 minus my 200 milliamp equal to 0. Like I said before, I'm going to tie it up, circle it, tie it up, and start writing my currents. That's how I'm getting these equations. All right. Next, I'm going to go ahead and write my supernode for my rightmost equation. My supernode on the right is going to read as 200 milliamp plus my V3 over my 500 minus my 0.003 V delta plus V4 over 200 equal to 0. Next, I'm going to realize that I have constraint equations. So my constraint equations are going to come from my sources. So I have a source right here, and I have a source right here. So when I'm going to write these, I have to be wary that I'm going to read my potential difference from my positive terminal, towards my negative terminal. So how I would write the first one is going to read as, or actually let's go ahead and write constraint 1. Constraint 1 is going to read as V2 minus V1 equal to 20 volt. All right, I'm going from my positive terminal to my negative terminal. Positive to negative equals to that voltage. Next, I'm going to write my constraint 2. My constraint 2 is going to read as V4 minus V3 equals to 0.4 V naught. Now, like I said before, it's important to make those approximations that, let's go ahead and write them up here just so we can keep referring to them. V2 will actually equal to V naught, and V3 will equal to V delta. So whenever you're seeing the V naughts and V deltas, don't be scared. They're real voltages that we can just represent as is in the circuit, and it'll make the math a little bit easier as well. So like I said before, I'm going to provide you with some tips and tricks. However, I won't walk you through the algebra on this one. So what I would do is I'm going to multiply by a common multiple. So I can go ahead and reduce these. So for this one, I decided it was best to multiply everything by 500 and reduce as we go. For this right here, I decided it would be best to multiply everything by 1000 because I have 500 right here and 200. 1000 is prime for both of those. So I decided to multiply by 1000 here and 500 right here. These equations right here, I don't really need to simplify them any further, so I'm going to leave them as is. Now, upon doing that, you should get a matrix that looks like a 5, a 2, a 1.5, a 0. 0, 0, negative 0.5, 2.5, negative 1, 1, 0, 0, 0, 0.4, lots of zeros, 1, and negative 1. And we're going to model it. Again, these are my V1 values, my V2, my V3, and my V4. My final result is going to be 100, negative 100, 20, and 0. All right, so like I said, I want to put more emphasis on writing these equations. The algebra will algebra. All right, so again, we're going to compare our mesh current and our nodal. So before, we saw that mesh seemed to be a bit more work, and we had to do a little bit more thinking to be able to organize our equations, especially when writing the currents for V naught and V delta and expressing them. Whereas with the supernode, we had to make two identifications, realizing that this is a supernode, this is a supernode. Therefore, again, we can tie it up, write a dot in the middle, and start writing currents out of it. All right. Like I said, this example was a pretty good example. Personally, I would use Nodal on this just because it's more efficient. All right. So keep that in mind whenever you're solving the circuits. Thank you.